Hey, this is the Swiftbird. I'm Yakov. In this series, I cover the key concepts of Swift, iOS app development, and everything in between. I'm basically building a quick reference handbook, which I can use as a refresher before an interview or something like that. And if it's helpful to you too, that's really great. In the last video, I presented a few most essential questions about computer memory in general. This time, I'm having a detailed look at how memory management works in Swift. I'll be talking about ARC, different types of references, and retain cycles. However, I left a couple advanced topics for another video. Subscribe to the Swiftbird so you don't miss the next episode. And if you find this one helpful, give it a thumbs up. You can also support my future work on this channel at the links in the description. With that said, let's have a look at today's first topic, which is ARC. In my previous video, I described the key principles of manual memory management, and you had a chance to see why it's not the easiest or most convenient way. Back in the days, there were no alternatives, but these days you have multiple approaches to choose from. One of them is reference counting, and it is the model used in Swift. Reference counting relies on the concept of references, which I explained in the previous episode. The key principle of reference counting is very simple. The object stays in the memory for as long as it's referenced by others. When no one references the object anymore, it can be safely removed from the memory. To make this system possible, each object has a counter, which increases or decreases in response to different operations. Here's an example. Inside this function, we create a new object. Because this constant is the only thing pointing to the object, its counter is 1. After that, we pass the object to another function. Doing so increments the counter, because now the object appears in another place, the second function's parameters. This object should remain in the memory at least until the second function is finished. When it is finished, the counter goes back to 1, because the object is still referenced by the constant. But once the main function ends too, the constant no longer exists. At this point, no one references the object. Its counter goes down to 0, which indicates to the system that this object is no longer needed, and its memory can be reclaimed for other tasks. I showed you this example in Swift, but reference counting in other languages works just like that. In the Clang compiler used by Swift and Objective-C, this implementation is called automatic reference counting, because, it's technically possible to make reference counting non-automatic, even though it defeats many advantages and makes the code less reliable. Now that you understand how RC works in principle, let's have a look at the way it's implemented in Swift and Objective-C. Back in the days of Objective-C, you had to manually put the retain and release calls whenever they were needed. I didn't work with it much because I was like 10. But even my brief experience updating old code showed me how easy it was to make a mistake. You had to add the calls in the right places and the right order, and then you had to balance them. So for each retain, you've got exactly one release. When a stripped-down version of ARC was introduced in macOS Snow Leopard, it solved the hardest problem with those calls. Suddenly, you no longer had to think about them at all. In Lion and iOS 5, Apple shipped complete support for ARC, which added a couple more features. Oh, and in case you didn't notice, this was all before Swift even existed. But regarding ARC, Swift and Objective-C have very little difference. So, when you enable ARC in Objective-C, and in Swift it's always enabled, you no longer need to write any retain release calls. In result, your codebase becomes smaller and easier to maintain, and you can focus on the parts that are really important, instead of dealing with the boilerplate. But if you had a look at the compiled app, you'd notice those calls have made their way back into the program. That's because the most important step of memory management takes place even before any memory is allocated. At compilation time, the ARC compiler analyzes the code and actually inserts the missing retain and release calls. These instructions are responsible for managing the object's reference count. And when the app is running, the ARC runtime systems observes the execution and reacts to changes in reference counts. That means it's known when objects should be removed from memory even before the app launches. The runtime then basically just monitors the reference counts, and when one of them reaches 0, the system frees up the memory. Sounds genius, right? Indeed, automatic reference counting solves the majority of memory management problems. And unlike garbage collection, ARC has very little performance impact at runtime. I guess that's why it was adopted on iOS, back when devices weren't as powerful as they are today. But if ARC and reference counting in general look so good on the surface, why aren't they used everywhere? Are there any potential dangers which make automatic reference counting not entirely automatic? That is the next topic. Let's talk about retain cycles. They are probably the biggest, if not the only hidden danger of using ARC. To illustrate a retain cycle, I use this classic example with the bank. So, you've got a bank which issues credit cards. It's a strange bank because it keeps the entire database in the RAM. But the government is okay with that. When a new customer opens an account, the bank adds their data to its database and issues a new card. At this point, the bank has references to both the customer and the credit card. The digits here represent each object's reference count. The customer record keeps track of all the person's cards, but the card in turn has a reference to its owner. For example, when someone transfers money using card details, the transfer should update the total amount. Now imagine the customer decides to close the account and cancel all the cards. The bank does it and deletes the records from its database. However, the customer still has a reference to the card, and the card has a reference to the customer who owns it. Can you see what happens next? Nothing, and that is the problem. Because the customer and card objects have references to each other, ARC assumes they are both still needed and should remain in the memory. That's obviously not true. We can clearly see that these objects are useless at this point. We call this situation a retain cycle or reference cycle. In a real scenario, this could be a view controller which needs to perform some action at a later point. The view controller has a property with a closure, and the closure uses some property of the view controller. Because closures in Swift are separate objects, we've got a retain cycle. So even when the view controller is long gone off the screen, it still occupies some space in the memory, and so does the closure. Detecting a retain cycle can be difficult. Fixing it, not so much. The idea is pretty simple. What if we could somehow mark the reference so it doesn't affect the count? This way, we can still access the card's owner or the view controller using the property, but this reference will not prevent the objects from deallocating. You won't be surprised to learn that we can in fact mark those references. Now, everything I explained so far is relevant for the default type of references in ARC. It is called strong because it keeps a firm hold on the referenced object. This firm hold enables all the assumptions and guarantees I talked about. The object will stay in the memory for as long as it's used by another object. But once the last reference is gone, the object is immediately destroyed. But as you can see, there are corner cases, like the one I described in the previous section. And Swift provides a few more types of references to handle those scenarios. But how many is up for debate. To fix a retain cycle, your only concern is whether the reference affects the count. In this respect, there are two kinds of references, strong and non-strong. The conventional documentation says there's three, because non-strong references in Swift can be weak or unowned. I'll get back to their difference in the next section. However, there are two flavors of unowned references, safe and unsafe. The second flavor is extremely hard to find in any code base, but it does exist and have its own purpose. I'll explain it in detail in my video on advanced memory management, so subscribe to the SwiftBird. So my default answer is ARC has three types of references. But let's go back to our bank example. If the card uses a non-strong reference to point to its owner, that means nothing prevents the customer from being deallocated. You can end up in a situation where the card still exists, but the customer doesn't. Let's say an ATM is using the card, and at the same moment the bank closes the account. The customer object goes away, and so does its strong reference to the card. But because the card is retained by the ATM using another strong reference, the card's counter is above 0, so it stays in the memory. The ATM is now trying to read the amount, but the customer object no longer exists. What will happen when the app requests a non-existent object? That is where the difference between weak and unowned comes into play. So, if an object is not in memory, it can be read. That is pretty clear. But to weak, this scenario is pretty expected, and to unowned, it's an exception. When you use a weak reference and it cannot find the object in the memory, it simply returns nil. This feature of weak references makes working with them really easy. You use all the familiar techniques, such as optional binding. But sometimes you're absolutely sure the object will never try to access the other one when it's gone. In the view controller example, the closure executes when the user taps the button. So, if the view controller with the button is no longer shown, the user can't possibly tap that button. Unowned references were designed exactly for these cases. Using them is more straightforward, because you don't need to unwrap optionals. But if you somehow end up accessing a deallocated object, the app will crash. Because this situation is considered an exception, which should never occur. And I'm talking about the safe flavor of unowned. You may say it's better to be safe than sorry, so unwrapping an optional is not a big deal. And I agree. However, there are some differences in implementation, which make unknown references a bit more efficient. I'll get back to this in my next video, so stay tuned. And for this one, there's one last topic I want to cover. In the previous sections, I've basically mentioned all the pros and cons of ARC. But because it is something asked in interviews very often, I'll summarize them for you. Automatic reference counting is great, because it solves the majority of manual memory management problems. That includes memory leaks first and foremost. ARC guarantees that if an object is no longer used, it won't waste any memory, or worse, get exploited by attackers. Because ARC tracks individual objects and knows exactly when the last remaining reference is gone, the system makes memory management efficient, because it doesn't need to go through the entire memory graph and check every object. As a developer, you get a huge benefit in the form of smaller and simpler code. Instead of thinking about retaining and releasing, you can focus on the app features. However, the benefits of ARC come at a cost. The main one is the engineer's efforts. Acing ARC takes time and skill, and without really understanding how the system works, it's very easy to make a mistake which erases all the benefits. The general principles of ARC are pretty simple indeed, but it also has some intricate aspects. For example, loops may result in inefficient memory usage, and unless you know about the auto-release pool, you can accidentally create more problems than even in the manual mode. ARC also imposes some overhead, both at build and runtime. Personally, I don't see the compile time overhead as a concern. You build the app only once, and then it runs many times on many devices. At runtime, ARC is really efficient, but it still needs to monitor the reference counts and free the object's memory. For apps which allocate and deallocate a lot of objects, these can become noticeable. I guess that's why the latest Swift update offers you more control over the object's lifetime. That is intermediate memory management in Swift. I collected some of the most frequently asked questions and answered them in a short but detailed way. If you have more questions, I'd love to see them in the comments, and I may be doing a follow-up video later. That's it for today's episode. If you found it helpful, give this video a thumbs up and subscribe to the channel. You can also support the SwiftBird at the links below. I'll see you soon, and until then, make your skills fly.